In this video, I will talk with you about recommender systems. Let's take a loan recommender system as an example. Given a dataset, the columns are the lenders from lender 1 to lender 5, and the rows are the loans from loan 1 to loan 5. We denote N lender, the number of lenders, N loan, the number of loans. Rij is equal to 1 if the lender J rates loan I, and Yij is the rating by the lender J to loan I. Assume that loans may be for different purposes, for example, for business, education, personal use, and etc. What if lender 4 did not rate loan 3 and lender 5 did not rate loan 1? How can we predict missing ratings? Let's assume further that there may be NC purposes. So for each loan, there is a vector containing x1, x2, etc. up to xnc. And here I've just corrected several typos. So in the vector x, there should be 1, x1, x2 up to xnc, not x1 and x1. If we assume that there are 3 purposes for loans, such as business, education, and personal use, then the vector x transpose would be something like 1, x1, x2, and x3. If we can somehow measure the features x1, x2, and x3 for each loan in x, we can learn the lender's preference theta. Assume that we have features x1, x2, and x3 like this for the loans from loan 1 to loan 5. So, looking at the table, for example, for loan 1 is used for education, and loan 2 is used for business. The rest, which is from loan 3 to loan 5, actually have different widths on the 3 different purposes. Now this is a content-based recommendation problem. Each lender rating is a linear regression problem. For lender J, we learn a parameter theta J, and the rating is theta J transpose times Hi, and that is the rating of lender J to the loan I. So for example, assume that we learn a parameter vector theta 1 transpose, which is containing 0, 10, 0, 0 for the lender 1. And for loan 2, the vector x2 transpose is 1, 1, 0, 0. Then the rating is theta 1 transpose times x2, which is equal to 10. Now we need to learn the parameter theta j for the lender J. Theta j transpose times xi is the predicted rating of lender J to the loan I, and I or Yij is the real rating. So taking the difference and square it and sum over all the I loans where Rij is equal to 1. Here it means that we need to sum over all the I loans such that the lender J gave the rating. So Rij is equal to 1 where the loan I is given the rating by the lender J. And again, the number 2 here is just to facilitate the gradient term after the derivative. A regularization term can be added, and NC here is the number of categories, and here we minimize the whole thing for just the lender J. We can remove mj from the cost function, and now it becomes this. To learn the parameters for all the lenders, then we need to add another sum term. And this is a sum for all the lenders. And n lender, this is actually n lender, is the number of lenders. And here we minimize, we find thetas for all the lenders. From the cost function, we can calculate the gradient term. Taking the derivative of the first term, we get this. And here we have xki. It is because we take the derivative of theta j transpose times xi, and that's why we get this. Once we have the gradient term, we can form the update rule. So this is the update rule for theta naught and theta k for the lender j. And you can notice that we do not apply regularization on theta naught. With content-based recommendation, we need to somehow measure the features, and it is hard in practice. Given theta, can we learn the features? So this can be done with collaborative filtering. For each loan, for example, loan I, we try to minimize an objective function. And here we sum over all the lenders, where all ij is equal to 1, meaning all the lenders that give the ratings to the loan I. And here we try to minimize the objective function by changing xi. And again, for all the loans, we need to sum for all the loans by adding the sum from 1 to n loan here and there. So given the lender's preference, which are theta 1 for lender 1, theta 2 for lender 2, etc. Theta n lender for the lender n lender. We can find the features h1, h2, etc. up to xn loan by minimizing this objective function. And previously, given the features, we can find the lender's preference, theta 1, theta 2, theta j up to theta n lender by minimizing another objective function. So we can combine both problems and form a new optimization problem. And this is the new objective function that were combined from the other two. And here we find the features as well as the preference altogether. From here we calculate the gradient to form the update rule for the gradient descent algorithm. The first rule is for updating xki, and the second rule is for updating theta kj. The term inside the parenthesis is actually the gradient of the cost function with respect to xki, and the other is also the gradient of the cost function with respect to theta kj. The predicted rating by lambda j for loan I is theta j transpose times xi. It can be expressed by the matrix product of x and theta transpose. X has xi transposed on its rows and theta has theta I transpose on its rows.